Okay, in the last class, we had finished discussing the concept of signals, signal processing. We had also defined what does the digital signal processing word mean. And what we want to now discuss is why do we want to do digital signal processing as opposed to analog signal processing? And there are many reasons for that. We'll try to list a few of those reasons. So let's ask the question, why DSP? And some of the key reasons are, the biggest reason is repurposing of the hardware. So if you do this processing in the digital system, inside a digital system, all you are given is a processor and you program it. And let's say tomorrow you want to use the same processor for some other purpose. What do you have to do? You simply change what the software is doing. So that's, at some level, you can think of it that Instagram wants to do a better filter, which is filtering in Instagram is nothing but signal processing. It wants to do a different filter. What does it do? It puts out a new version of the app that you can download, and now you can do better filtering. So repurposing is a big, big reason for the. So the first thing is repurposing of the hardware. Okay. One of the other reasons is ability to correct errors. So if you are doing analog processing, what will you have? You will have capacitors, resistors, inductors on some sort of a PCB. And if you detect an error in that, what needs to be done? You'll have to throw out that PCB and start anew. Okay. Whereas in the digital world, if you found an error in whatever you were implementing, again, all you have to do to fix that error is perhaps rewrite your code. So DSP systems are much more easier to deal with when it comes to fixing the errors. So one of the other characteristics is errors can be easily fixed. Okay. The third thing, which is one of the biggest plus, is mass production of systems. In analog world, no matter how precise you end up being, if you have ever done experiments on breadboards, for example, where you read the instructions of the resistances, it says, well, we expect it to be a 100 ohm resistance, but within plus minus this percentage ohms. Or this capacitor has this much capacity, but within certain ranges. No matter how careful you are in analog systems, no two analog systems will end up being exactly the same. There will be some variations in them. On the other hand, digital systems, you can mass produce them and each one of them will do exactly the same thing. Okay? So if you buy 1,000 iPhones, for example, and if you perhaps record your sound in that iPhone and then listen to it, all those 1,000 iPhones will work exactly the same fashion. Okay? So mass production, and that is one of the key reasons, mass production of devices is a big reason. And the last one, which is we all know because we have these iPhones and iPods and other DVDs and stuff, is when you have digital systems, the signals that you have, of course, need to be somehow brought into the digital world. But once they are in the digital world, you can store them for an indefinite period of time. Okay? As long as you maintain the integrity of the bits. There is no gradual degradation. I don't know if you guys are all too young, but maybe you have seen magnetic tapes for recording music or videos, they do degrade with time. Right? And whereas in the digital system, as long as you can preserve the integrity. Now, of course, if you scratch your CD too much, you will lose. So it's not completely error resilient, but storage of media is another key. Storage of digital signals. And combined with that, basically, what is helping all of these advantages is the Moore's law. What's the Moore's law? Roughly speaking, what it does is that you can pack more and more transistors onto the same chip, which means your processing power, your digital processing power is increasing. And not only that, but also digital systems are becoming cheaper and cheaper and cheaper. So whereas if you had to build a system in analog, it may require you a lot more money, a digital system can be very easily built. Okay, the cost is going down. So all these advantages, when you couple them with the market forces, basically propel you towards the digital systems. So these are the advantages. The question is, are there any disadvantages? Is DSP always better than analog processing? Despite all the advantages of DSP systems require processing in the digital world. Now, most signals, for example, I'm disturbing the air pressure is changing, and you are listening to it. It's an analog phenomenon. My eyes are looking at the scene, that's an analog phenomenon. So if you want to do digital processing, what is the first step you have to do? You have to somehow convert that analog world into the digital world, which is called sampling, which we'll learn about a little bit. Now, once you do the sampling, while we will learn about theoretically, you can ensure sampling loses no information. Practically, the conversion from the analog world to the digital world is always going to cause some loss of information. Okay? So anyone who says digital music is the best music, right? It's with a lot of caveats. That's not true. Because the moment you had a song on a CD or a DVD or an iPod, you have lost some information. Now, the loss of information is so negligible that you wouldn't happen to care. But there are advantages, and the first key advantage is that loss of information due to sampling. And with the sampling, so sampling is just conversion of the digital system of the analog world into the digital world. There is another thing that happens in the digital world. How is information stored in digital systems? It's stored in bits. Right? So if you have 1 bit, how many different pieces of information 1 bit can store? It can store either 1 or 0, 2. Right? So in general, if you have an 8-bit system, it can store 2 to the 8, which means if I am speaking, my voice is going up and down, and your ears can register all the variations in my voice because I'm speaking analog, and your ears process it in an analog fashion. But inside a DSP system, you can't store all possible variations of my voice. Why? Because a DSP system requires a finite number of bits. So if a DSP system is 8-bit, you can only store 2 to the 8 or 256 values. Okay? If a DSP system is 32-bit, then you can store 2 to the 32 variations. That's a large number, but it is still not every possible variation. Okay. We'll of course look at it more in detail. So the first disadvantage is due to sampling. The other disadvantage is called quantization, which we will learn about more. But DSP systems, the term that is used is they suffer from finite precision. You cannot represent something infinitely close to what exists in the analog world, the value. Okay. And then there is a third reason, which is the power related reason. We all know when we use our iPhones or other smartphones, what happens? They lose battery power and soon they die. Okay. In general, digital systems tend to consume more power than analog systems, especially if you have an inductor or a capacitor. Right? The amount of power that they lose is much smaller than DSP systems. DSP systems require considerable wattage for them to be able to operate because you are running this microprocessor and these switches are opening and closing. Okay, so DSP systems require more power. So we have advantages, we have disadvantages, and then the question becomes, well, are the advantages good enough that we can ignore the disadvantages? And the answer is yes. The disadvantages, while they are there, they are much smaller in size than the advantages, and in general, some of those disadvantages are becoming less and less important because of, again, kind of the Moore's law. Like, it used to be that if people had 8-bit systems, they would be very happy. Now, the processor in the iPhone 5S, that's a 64-bit processor. Right? So it can hold 2 to the 64 different values, for example. You can use that processor to do any kind of signal processing that you want. Okay? So the disadvantages are much smaller, and they are, because of that, we do want to stick with DSP. So I want to complete this introduction by giving a big picture view of DSP in the context of our class. And I'll try to explain what we will be learning. Again, as I said earlier, what we are going to cover in our class is going to be a very, very tiny fraction of what signal processing systems in reality can do. Okay. So DSP systems, as we talked about, there is always some underlying application that you are interested in. So what we start off with, we have some physical or man-made phenomenon that we are interested in observing or manipulating. So a physical phenomenon could be that you are interested in measuring, for example, the seismic activity. A man-made phenomenon can be that you are interested in measuring Facebook interactions of people on Facebook. And the first step in any DSP system that people ask is, this is a phenomenon, how do we measure it? How do we acquire it? Okay. What things we should be measuring and what things we should not be measuring. So the first question that you ask in DSP is how to acquire the phenomenon, observe the phenomenon, measure the phenomenon. You can call it whichever way you want. Okay. And the answer most of the times lies in the the field of signal processing or the sub-area of signal processing that's called sampling theory. Okay, it's called how do you sample it. Now this sampling often happens through a device which could be a combination of hardware or software and software. Okay. So one of the common devices that are used to acquire, for example, analog signals is called an analog to digital converter. You input the analog signal and it converts it, and we'll learn more about it. We'll learn some very basics of sampling theory in this class. Now, once you sample, what you get at the end of the day, regardless of whether you had an analog signal or something like Facebook interactions, you end up with a sequence of numbers, which is called discrete signal, which will, so at this is done at a device level, then you get a discrete signal. Okay. And the questions, once you have that discrete signal, the question you can ask is, for example, how to analyze the phenomenon. For example, let's say you measure the radio waves in this room because you are interested in finding out how is Wi-Fi data good or not good in this area. Now you have acquired those radio frequencies, now you want to do some sort of analysis. So there are many different ways. Again, that analysis is very much application dependent. In this class, we'll talk about a little bit of that under the term of DFT, which is called the discrete Fourier transform. We'll learn it later in the later half of the class, DFT-based processing. Okay. Sometimes you don't want to do the analysis. Sometimes you want to just manipulate the signal. Again, the input is a discrete signal. And the question you are interested in asking is how to manipulate the signal. Like you have some song and you want to increase its bass or treble. That's a question of how do you do the manipulation, and the answer lies in digital filtering, which we will learn in this class. There are many other ways. Okay. For example, if you have seen some of those websites or some of those apps where they take your image and they generate, if you take an image, they generate, for example, an image which looks like a pencil sketch. Have you guys seen those kinds of apps? That's a signal processing operation, actually. Okay. We are not going to talk about image processing aspects of signal processing, but that's the kind of manipulation that you can do. Okay. It's effectively a filtering operation that you do. So if you get good at filtering of images, you could write your own app on Android or iOS to do all kinds of manipulations that you see in today's world of apps. Okay. And at the end of the day, what happens is in some cases, not all cases, you are interested in, after doing that manipulation, for example, you take my sound and you want to do something with it, and you, at the end of the day, you may want to reproduce that phenomenon. Okay? So if you record my voice, the goal is you want to play it back to someone. Now, you started with the analog world, you converted it into a digital thing. You have to now, if you want to play it back, you have to again convert it to the analog system. Okay? So that sometimes that is required, and that's the part becomes how to reconstruct the phenomenon after all this manipulation or sampling. And the answer again lies in sampling theory. It's called reconstruction, which is part of sampling theory. Okay? And this reconstruction again involves some sort of a device, hardware-software combination. In your labs, you will see these devices. They are called analog to digital converters, digital to analog converters. Okay. So in our class, we'll be focusing on some of these questions. We'll first be doing sampling theory and reconstruction of sampling theory. Then we'll be talking about digital filtering, DFT-based processing, and so forth. I want to end this discussion with saying, what is this class about? If you want to understand these operations, we really have to understand the mathematics of signal processing. Signal processing is a sort of a different kind of a beast in your undergraduate education, because there are some courses that you will take, for example, let's say programming courses, where there is less mathematical foundation of that course. Okay, and then there are some courses that are all mathematics, like let's say you take a calculus class. All people want to do is make sure you understand how to do these calculus problems. Signal processing is really a marriage between those two concepts. It involves abstract, deep mathematics, and there is no way you can learn signal processing without understanding those mathematical underpinnings. So that is what this class is about. We are going to teach the mathematical underpinnings of signal processing. Okay. Even though the area may sound fancy, or I can go ahead and do manipulation of images or signals or do maybe analysis of financial data, but none of that can be done before you understand the mathematical principles that help you do signal processing. So this class is really understanding those mathematical underpinnings and then trying to connect to certain level, because we can't do all of them. The final project will help us make that connection a little bit clear. So trying to connect that to the real world, which will mostly be covered through lectures and then you asking me questions. So mathematical underpinning and connections to real world. And if you only focus on math, you actually, again, would not be able to do a good job of making use of this signal processing class, because it's really, you're thinking about the real world application, thinking, how can I use what I have learned to solve this problem? Okay. And what this class is not about is about hardware. I'm not going to teach you any hardware related stuff. There are classes that are offered which are like VLSI for signal processing or things like that, where they teach you how to build, for example, digital systems, but this is what this class is not about. So I want you to be sure what this class is about and hopefully get you in the right mindset. So we will end our introduction here and we will move on to a little bit of review of the signals and systems class at a very fast pace. Okay, so now we want to talk about very briefly some of the basic concepts of signals and systems that you must have learned in 345. And we are now going to be talking more mathematics than intuitive understanding of or applications of these things. Okay. So signal, we already understood heuristically what it means. Now, from the perspective of signal processing, mathematically, what is a signal? A signal is nothing but a function of one or more independent random variables. So a function of one or more independent, I said earlier random, they need not be random. So just one or more independent variables, and the function can take either real values or complex values. Okay. So that's the mathematical definition of a signal. Now, as I said, if it can be a function of one or more variables, independent variables, and depending upon how many variables are used to describe that function, we call that function either a 1D signal, a 2D signal, 3D signal, and more than 3D signals are also possible. So 1D signal, a perfect example of that. So it's a function of one variable. We typically write x of t. You should be clear about the fact that all this notation is dummy, right? I can call my signal x of t, I can call it y of t, I can call it z of t, and the independent variable t is also dummy. I can call it x, I can call it y, whatever, right? Mathematically, a function, all it needs is the independent variable and the value it takes. So x of t is a 1D signal, and a typical example of that is speech signal. When I speak, if you were to use a mic, well, instead of the pressure waves, we'll talk about the mic because it will be easier. You have a transducer. I'm speaking into this mic. What is the mic doing? It's generating electrical pulse, which is the variations of that pulse tell me the variations in my sound intensity. Okay, so as time goes on, that signal goes up or down. It's a function of one variable. Okay, now you can have 2D signals or functions, for example, f of xy. And you probably did not see them in 345. I just want to point out to you. For example, if I am working at, let's say, Weather Channel, and I map the temperature on the surface of the Earth, okay? So I can say that this fxy, this function is the temperature as a function of surface of the Earth can be described through two parameters, longitude and latitude. So this fxy as a function, temperature as a function of longitude and latitude, and latitude is a 2D signal. Okay? It's giving me information. Somewhere the temperature is 22, somewhere it's 101, and so forth. And as a function, I can map that. Right? So I have that 2D function. I can have even 3D functions or signals. For example, g, x, y, z. Let's say that I am interested in mapping the atmospheric pressure on the entire globe, and also in terms of the height. Perhaps I want to give that information to airlines. Right? So what are the three parameters that describe that? I have longitude at this point, and I have latitude at this point on Earth, and I have elevation. Right? So on this point of Earth and at this height, the atmospheric pressure is this value. Right? So pressure as a function of longitude, latitude, and elevation, that's a 3D signal. An image is a 2D signal. A video, black and white video, is a 3D signal. If you want to talk about more dimensions. Actually, an image really is made up of red, green, and blue colors. So in fact, it's 2D for red, 2D for blue, and 2D for green. Okay. So I just want to make sure you understand that when we say signals, it's not just limited to 1D. Now this class, though, will be about 1D. This will be about 1D signals. Extensions to more than 1D are sometimes there are some mathematical trickeries involved, and sometimes it's a simple extension. Okay. The other question that comes up often in signals is, what do we mean by a complex signal? Because everything in the real world is just real. Well, you should think of a complex signal as a mathematical abstraction to represent a signal which has two components that can't interfere with each other. So if you have a complex number and you add two complex numbers, what happens? Only the real number gets added to the real number, and the imaginary part gets added to the imaginary part. Right? At this stage of the class, it will be too involved to describe how do those complex numbers arise in the real world. But what you should think of them is, if you are given a signal, let's say x of t, which has two components, a of t, which is real, plus j b of t, which is complex, you should really think of them as two separate signals which cannot interfere with each other. They are separated from each other through this complex, this j factor, square root of -1. Okay, that will be the easiest way to think of it. How they are generated, they actually arise quite frequently in, for example, communications applications, and you will learn them if you take, for example, communication systems. I presume either in this or the next semester. But if it becomes too complicated, just try to remember that at some level it's saying the signal has two components which cannot interfere with each other. Okay, so complex numbers or complex signals are not just a figment of any academic's imagination. They really do exist, and they are a mathematical abstraction of what we do in the real world. Okay, so I'll leave it at this point, only up to this. So this class, as I said, focuses only on 1D signals, and the independent variable, we will implicitly say it's time. Now, you should make sure that you understand this aspect, that whether you have time or not is immaterial. Okay, mathematically, if you think about it, if I am doing any mathematical manipulations of a function, right, let's say I'm doing integration of a function, mathematics doesn't care if the independent variable is time or maybe length or something else. Okay, so by the same token, you should try to remember that as long as something is 1D, everything that we are learning in this class is applicable to 1D signal processing. We are just using the example of time so that we can make sense of most of the signals. But let's say if I were to measure along the length of this table temperature, that will be 1D signal. I'm measuring just what is the temperature at this point, at this point, at this point, just one parameter. Okay, everything that we will learn about 1D time signals will be applicable to that kind of a signal too. Okay, so Very important to remember that. Abstract mathematics doesn't care whether it's time or not. Okay, so once we talk about signals, then mathematically there are two main types of signals. We can divide them into two broad classes. The one is continuous time signal. So what that means is that you have a signal whose independent variable takes any value on a continuum, or the function or signal is defined on a continuum. So a continuous time signal is defined as, it is defined on a continuum or defined for continuous values of the independent variable. And in notation, we always use these parentheses to demonstrate that the independent variable takes any value on a continuum. Okay, now a continuous function by its very definition is defined everywhere. Okay, so if I x of t, I have this as e to the minus at for t equal to 0, right, and equal to 0 for all t not equal to 0. This function is defined for all values of t, even though realistically, if you just look at it, it is nothing but just one. It has at 0, it has value 1, and everywhere it has value 0. But it is defined. Okay, just having the value 0 doesn't mean it's not defined. You can say, what is the value of this function at t equal to 100? And the answer is 0. Right? On the other hand, the other class of functions that we have is discrete time signals. And the idea is that in discrete time signals, the independent variable only takes certain values, which means your function is defined only for certain discrete set of values. So the notation that is used to write that the independent variable is discrete. Okay, when we say continuous time or discrete time, it's really talking about the properties of the independent variable. So we use these square brackets, and the variable can be anything. So typically we write it as n. Okay, so x of n, and the function or the signal is defined on a discrete set of values. Now typically we take these n's, these independent variables, to take values of all integers, -1, -2, -3, 0, 1, 2, 3. Okay, that's just a convention. In general, a discrete time signal is nothing but a sequence of numbers. And the independent variable, all we are asking is that it's on a discrete set. So a discrete time sequence, for example, if I say my n is 0, 1, -1, and I define xn, for example, equal to, let's say, 1 for n equal to 0 and 0 n not equal to 0. Okay? What is the major difference between this function that I defined, x of t and this xn, even though they both take values 1 at 0 and 0 everywhere else, what is the difference? The question of what is, for example, x 0.3. This does not make sense. The signal is not even defined. You can't say x 0.3 is 0. It does not exist. We don't know what it is. Okay? So that's the key difference. Between two values, we don't know what the signal is. It's not defined. Okay? So what is x 0.3 does not make sense in the discrete time world. Okay? So you need to be clear about defined and perhaps the function being 0 at a point. So if ever you are given a question like that, please don't write x 0.3 equals 0. Okay, another thing that I want to clarify, which is not entirely clear when you take 345, is that talking about whether a signal is continuous time or discrete time is really talking about what does your independent variable do. Okay, it does not talk about what does the amplitude of the signal does at those values. So to give you an example, this is a continuous time signal, okay? And this is a continuous time signal too. Why? Because the fact that a signal is continuous time or not is really a function of how does your x-axis behave. Whether your independent variable, your x-axis, is your function is defined on every value of the x-axis or for every value of t if you want to think about it. But it does not say anything about, so the question of whether the amplitude takes all possible values, so this is all possible values sort of between 0 and 1, or it takes only two values in amplitude. So this is, let's say if this was 1 and this is -1, two amplitude values. Okay. When I say continuous time, it does not differentiate between the two. Now, in the engineering world, this kind of thing where not only your independent variable is continuous, but also your amplitude can take any values in between. That is called, this type of a signal is called an analog signal. And that's the difference between the word continuous time versus analog. Analog means your x-axis is continuous and the amplitude that your signal takes is also continuous. Okay, perhaps within a range, but it takes every possible value. Whereas this kind of a signal is called, its amplitude takes only a finite set of values. Okay, so this is not an analog signal. Similarly, in the world of, when we talk about discrete time, we are only saying what happens to the x-axis. So let's say if this was 0, 1, 2, 3, and so forth. This is a discrete time signal. And if I say that actually the values of this discrete time signal can take any value, Okay, if x0 can be any number, then this is a discrete time signal but with continuous amplitudes. My amplitude of the signal can be anything. It's not restricted. On the other hand, I could say that my discrete time signal only takes, let's say, is only allowed to take values 0, 1/2, and 1. So my discrete time signal is either 1, or it's 1/2, or it's 0. Okay, and it can't take any other value in the amplitude. 1, 1/2. This is a discrete time signal too, but now its amplitude is also discrete. It can only take finite number of different values. Now, in terminology, this kind of a discrete signal is called a digital signal. So the difference, whereas this is not a digital signal, it's just a discrete time signal. I want to make this distinction clear. Most of the times in this class, we will be talking about discrete time signals, not digital signals. A discrete time signal gets converted into a digital signal through the operation called quantization, which we will study later. Inside your computer, of course, you can only have digital systems. Why? Because a computer can only store so many values. If it has 2 bits, it can only store 4 different values. Okay? Okay, let's now move our discussion to systems. So heuristically, we talked about a system being anything that takes as input and produces an output. Broadly speaking, we can divide our systems into many different versions. So I'll use T to represent a system, which is a black box. Okay. One variant of the system is, and in this class, I will focus only on systems which take one input and produce one output. Okay. But you can have systems which take multiple inputs. We talked about the example of, for example, Skype calling, where it's taking the input of both your voice and the image. Right? So it's a 2-input system. But we'll, in this class, only talk about one input, one output, and a system can take continuous time input and generate a continuous time output. An example of that system will be a cell phone. I speak, it's a continuous time signal, and the cell phone generates radio waves, which are continuous time signals. A system can also take discrete time inputs and generate discrete time outputs. Okay, so it takes discrete time input, discrete time output. An example of that will be something like a software which manipulates images, for example, Photoshop. Okay. You give it an image inside a Photoshop, which is discrete, although it's 2D, and you say reduce its size or do some other operation on it, and out comes another image. Discrete input, discrete output. Okay. Those are, of course, what you would expect, but you can also have hybrid systems which take, for example, a continuous input, x of t, and they generate a discrete time output. So continuous input, discrete output. An example of that will be a digital voice recorder. I'm speaking, that's a continuous input, but the digital voice recorder is going to store that inside the flash drive of that recorder. That will be just a sequence of numbers. So it will be a discrete time signal. Okay. So a voice recorder, which is digital, is an example of that. And then this is, of course, everyone's favorite, at least I'm sure you use it, you may not realize it, xn, which is discrete input, but the output is continuous. So an MP3 player is a perfect example of a system which takes input in discrete time and produces a continuous time output. Okay? We will mostly be concerned with, in this class, this example of discrete input, discrete output. We will be relating that to the continuous input, continuous output systems. And the other two ones, we'll just briefly talk about them, but we'll mostly be talking about them in the context of building DSP systems and not necessarily the relationship between inputs and outputs. Okay, so these are types of systems. Now, a system's mathematical model, if you want to talk about a system, the most important thing is you understand what the system is doing to the inputs to produce certain outputs. And in general cases, for arbitrary systems, it's very hard. I gave the example earlier of, for example, brain or the physiology of a human body. Everything that goes inside us, that's a system. Okay? We are taking inputs from the real world and our body is reacting to them. But mathematical capturing of that system is extremely, extremely hard. Okay? So what we will study in this class will be the simplest forms of systems. The simplest and most often, which you have already done, and most often used systems, they are called linear time-invariant systems. So linear time-invariant systems are those that obey two properties. That's all. We are not interested in physically what does the system look like. Does the system process voice? Does the system process something else? We don't care. Mathematically, what we care is the system obeys two properties. If it obeys two properties, analyzing that system becomes super easy. Okay. The first property, as the name implies, and I'll be using LTI for abbreviation. The first property, as the word implies, is linear. So the system can be just linear, it can be just time invariant, but when it's both linear and time invariant, that's the best kind of a system in terms of analysis, not in terms of necessarily all processing. What is a linear system? We all studied that in the previous class, but just a quick reminder. A linear system is one in which principle of superposition applies. What is the principle of superposition? That if a system takes one input and generates another output, right? So you have some, and I will be focusing right now on discrete, on continuous time systems. I'll be writing my inputs and outputs as continuous time. Just keep in mind that the same applies to discrete time, but I just don't want to write it twice. So if you have a system T, which generates output y1 of t, okay, and it has another input, and these inputs could be arbitrary, okay. What I mean by arbitrary is that as a rule, this applies no matter what the input and output is. So if a system does this to two inputs and out, given an input generates an output, given another input generates another output, and if you were to superimpose the two inputs by adding them up, at the output you get just the superposition of the outputs. That's the principle of linearity. Okay? So at some level, up to a certain extent, for example, so let me just write the mathematical definition. If mathematically what is written is that if I have a x1 of t, where a is any scalar, real or complex, plus b x2 of t, and I pass that to the system, then all that happens is that my outputs get scaled by the same numbers and they get added. We experience this linear system inside our body up to a certain level all the time. The perfect example of that system is human ear. Okay? If one person is speaking, I can hear them. If now another person starts speaking, I can hear them. And if both of them start speaking simultaneously, what do I hear? Superposition of them. Right? So that's what the linear system is. You simultaneously generate the inputs, the outputs just get superposition of those inputs. Superposition of inputs generates superposition of outputs. A very simple principle, linearity. The other principle is time invariance. Time invariant systems are effectively saying that the system is static up to a certain level. So it implies static nature of system output or of system characteristics. Heuristically, you can also say that output, what a system generates as output, is only a function of the input and not a function of when that input was applied. Okay. So output depends only on the input and not on the time at which it was applied. So if you have, let's say, today I apply input to the system and I get y of t. And let's say I come back to that system 2 days later and I apply the same input 2 days later. Time invariance means that I should get the same output, but since I applied the input 2 days later, my output should be generated when? 2 days later. Okay, so if I apply x of t minus t0, what does this mean? That now I have delayed my input by t0 seconds. So let's say t0 was 24 hours. Right? My output will be exactly the same, but it will appear when? 24 hours later. Okay, so it will be y of t minus t0. That's the principle of invariance, time invariance. Okay, what it says is that up to a certain extent, the system is not changing. If I use my voice recorder today to record a voice, or I use it 3 days later, it's going to generate the same output. You need to understand the mathematics, but it's important for you to understand what heuristically time invariance means. Okay. So a linear time invariant system is a system which has both these properties combined. If you give it superposition of inputs, it generates superposition of outputs. If you give it input today or 10 days later, it's going to generate the same output, but with the same delay. If you input it 5 days later, the output will be generated 5 days later, but the nature of the output will exactly be the same. So the question that arises is, why do we care about LTI systems? Why are LTI systems good, quote unquote? Again, they are good in terms of analysis and the fact that many real-world phenomenon can be modeled as LTI systems. Okay? If you have a voice recorder, you can't expect that voice recorder to keep on performing the same way 1,000 years from now. So technically, it is not a time invariant system. But the time span over which it changes, it's so large that you can consider it time invariant. Okay? Similarly, the linearity property. So why are LTI systems good? Well, it's because of the following reason. In general, if you want to specify a system, if you want to say, here is a system, tell me what it does. What do you need? You need to be able to specify each input-output pair. You better be able to tell me if I input this quantity, I will get that quantity. Each input-output pair has to be specified for an arbitrary system. Okay? But LTI systems have the property that you know the output to every input. You know the output to every input as long as you know the output to one special type of input. Okay? So knowing the output to one special type of input is enough to tell you the output to every possible input you can get into the system. So describing an LTI system becomes very easy. Okay? So output to every input can be specified as long as we know the output to a special input. Yeah. Please keep in mind, and I have to remind my class every year, that this is not true for every signal, for every system. This is only a property of LTI system. What is that special input? That special input is the impulse or delta function. Okay. So the delta impulse signal, which in continuous world you write delta of t, which is a mathematical abstraction. Hopefully everyone viewed that video that I assigned on delta functions. And in discrete world, it is delta of n, which is a very well defined function. So if you are given a system and you know it is LTI, that is the key. Typically what the notation is used is delta t or delta n, and the output of deltas is represented as either h of t or h of n. And as the name implies, right, the system generates a response. Now, h of t is generated in response to an impulse. So h of t is called impulse response because of that reason. Right? So h of t or age of n, they are called impulse response, which simply means that the system response when you apply an impulse is age of t and age of n. Every possible system in the world can have an impulse response. That is not what defines an LTI system. Okay? What is impulse response? I apply an impulse, I get a response. That's impulse response. Every system can have an impulse response. The property is that if you have an LTI system, then knowing this impulse response is enough to tell you what is the output to every input. And how is that known? If T is an LTI system, then if I input x of t, which is any signal, or x of n, and I'll talk about both, then the output is y of t or y of n, and the input output are related through the convolution formula. So continuous time world, y of t is given by convolution of x of t with the impulse response. All I needed was the impulse response, and now I know the output to every input by simply taking convolution of my input with the impulse response. This property is only true, I'm repeating it again and again, this property is only true if you have an LTI system. And that's the beauty of an LTI system. You know the input, you know the output to one input, you know the output to every input. In the discrete world, the output is again given by a convolution expression, y of n with age of n. And because of this reason that LTI systems are completely described by impulse responses, okay, we often write LTI system, instead of writing T, we write actually in the block, we write their impulse response. So you will get this kind of a notation, x of t, h of t, y of t, which simply means that the system is an LTI system and its impulse response is h of t. Okay. Or if you have discrete time, then we'll write h of n and it will say xn and y of n. And I'm sure all of you have studied convolution in your last class. We'll just do a quick reminder. So continuous time convolution and discrete time convolution, they are very similar, except that one involves integration because it's continuous and the other involves summation. So it can be written two ways. It's minus infinity to infinity, x of t minus tau, h of tau, d tau. Or it can be written as x of tau, h of t minus tau, d tau. Right? This is a mathematical expression. They are equivalent. The term that is used is convolution is commutative. It doesn't matter which term you put first, which you put second, just like summation or multiplication. And I hope you all know the flip and slide understanding of this expression. So what this is saying is that if you want to generate an output at time t, that is equivalent to you fix, for example, your one of the functions, it could be x or h, and then you flip the other one and you slide it by amount t. And then you multiply the two, take the integral, you get your answer. So here is a demonstration of that flip and slide rule of continuous convolution. This is your x of t. This is your h of t. In this case, we decided to fix x. So x of t is fixed. That is x of tau, right? It's just an independent variable. It doesn't matter I use t or tau. So this is fixed. Then I first flip. So this is the flipping operation. I flip around the x-axis. So this is h of minus tau. If I want to now compute the value at t1, then I slide it by the amount, either in this direction or in that direction, right? And then I multiply by the 2 and take the integral. So in this case, in this t1 example, the multiplication of them yields 0. So the integration is 0. And so the value at t1 is 0. Right? Now, for t2, I slide it this way by amount t2. And now I multiply the 2, and this green region is the multiplied signal. And now I take the integral, which is just the area, which is this region. I get the value this. So this is my value for t2. For t3, I slide it more. I get multiply the 2, compute the area, which is this area. I get t3. For t4, I again slide it by the amount t4 here. Multiply by the 2 signals, compute the area, and I get this value. And that's how you get every possible value on the t-axis. Okay. So that's the flip and slide rule. The discrete time version is very similar to this one. Instead of integration, we see summation, and we'll go over that in the next class.